We're going to take a look at sampling distributions for a mean in StatKey using the data set Hollywood movies and the variable budget. So to do this, we'll go to sampling distribution for a mean on the StatKey homepage, and then this is a data set and variable that we can select from the drop-down menu. Coming over to StatKey first, this is where we're going to go, sampling distributions, mean. And in our drop-down data menu, we can see Hollywood movies 2E budget right here. First, just looking at our population, we can see that it has pretty heavy right skew. This makes sense because there are some very high budget movies, but we can't really have a tail going as far on the other end because they all get cut off at 0. All budgets, of course, are at least 0. So we have a pretty heavy right skew, not extreme outliers in this case, but at least a pretty heavy right skew we would identify as our shape. We're going to start generating some sampling distributions, starting with n equals 5. So in this case, each dot in our sampling distribution is the mean of 5 different movie budgets, randomly selected from the population. So coming up here to choose samples of size n equals, I'm going to enter 5, and then I'll right away just generate a few thousand samples so that we can get an idea of the shape and get a reasonable estimate of the standard error of this distribution. It looks like we have lost some of the skew that was in our original population. This is now moderately skewed to the right, but not heavily. But that skew is definitely still there, and our standard error estimate is 24.045. Yours might be a little bit off from that. So we'll describe that shape as moderate right skew. And the standard error 24.045. Now we're going to go back and generate samples of size n equals 20. So we'll reset the plot, change the value of n to 20, and generate a few thousand samples. Now we have a standard error of 11.89, and we also have a distribution that's getting closer to bell-shaped. It looks like it's still got a little bit of right skew here, but not a whole lot. So we have 11.89 as our standard error, and a slight right skew remaining. Now we'll go to n equals 50. Again, generate a few thousand samples. We now have a standard error of 7.521. And we can also see that the skew is almost completely eliminated. We have a really nicely bell-shaped curve, a little outlier over here to the right, maybe a few, but almost entirely a nicely bell-shaped curve. So bell-shaped at n equals 50. So we can see two things happening as we increase our sample size. The sampling distribution gets closer to bell-shaped, and we also can see that the standard error gets smaller. So the amount of variability in our estimate of the mean gets smaller, and we end up essentially getting better estimates if we're talking about estimation. In this context here, we actually have the whole population, so we're just exploring and we're not trying to estimate anything, but the way that we end up using this ultimately is more for estimation of a mean based on a sample. So we're going to do this for another variable now. Also in the drop-down data menu, we're going to choose Hollywood Movies 2E, that's from the second edition of the logbook. This time the variable audience score instead of budget. So back to the data menu, Hollywood Movies 2E audience score. And I'm going to again start with samples of size 5. But first let's look at this population. Very different shape. I wouldn't quite call this bell-shaped, but I would call it close to symmetric and unimodal. The only reason I wouldn't call it bell-shaped is that it doesn't have those nice tapered tails. Especially over here on the right, it just sort of stops abruptly. On the left, we have a little bit of a tapered tail, but not quite bell-shaped. So samples of size n equals 5, a few thousand samples. This gets us something that's closer to bell-shaped. You see these nice tapering off tails on both sides. So with n equals 5, we have bell-shaped. We also have a standard error of 7.502. When we change n to 20, generate a few thousand samples, we still have a nice bell-shaped sampling distribution. Now our standard error is 3.695. Still bell-shaped. And of course, going up to n equals 50, we don't expect to lose that bell shape. Once that bell shape has been established, it's pretty much just going to maintain as you increase your sample size. The one thing that will continue to change as you increase your sample size is the standard error. We're now down to 2.303. So here we didn't really see a change in shape as we increased the sample size, but we did still see that same decreasing standard error as we use larger and larger samples to estimate that mean. So from these observations, the two distributions we looked at, is it always necessary for the sample size to be large? I would say from this last example, no. Even with n equals 5, we were already getting a really nicely symmetric unimodal distribution. But is it helpful for the size to be large? That's where maybe we'd look back at this other one where we didn't start out with something bell-shaped, but as the sample size increased, we got closer to bell-shaped. So here I would say yes. It is helpful. And if the sample size n is not very large, then what needs to be true of the population is that it has a similar shape to what we saw in our second example. So we want the population to be close to symmetric and unimodal. It doesn't really have to be perfectly bell-shaped, but what we want to see is that it doesn't have outliers and it doesn't have a really obvious heavy skew. Also, what happens to the standard error as the sample size increases? We saw that it decreases. The standard error gets smaller as the sample size increases. Remember that that's not saying as the number of samples we generate for the distribution increases. I can keep generating samples here for this distribution and my standard error is just going to stabilize. It's going to stay around 2.3 no matter what I do. It's really this n up here, which is the number of values that go into each one of those means increasing, that causes this standard error to decrease. So the context of that when we get into inference is really what's the size of the original sample that we're using to try to estimate this mean. This brings us to the central limit theorem for sample means. which states that if the sample size n is sufficiently large, the distribution of sample means from a population with mean mu and with standard deviation sigma is approximately, this n means normal, with mean mu. So what that tells us is the same mean as the population. And standard deviation sigma over square root of n, that is different from the standard deviation of the population. The population has standard deviation sigma. This sigma over square root of n is where that decreasing standard error as n increases comes in. The standard deviation of this distribution is the same thing as the standard error of the sample statistic x bar, right? We're talking about x bar here because we're talking about a distribution of sample means, and we always call sample means x bar. And so this sigma over square root of n gives us a formula for how rapidly that standard error decreases as n increases. So the standard error is smaller for larger values of n, approximately according to this formula, the original standard deviation of the population divided by the square root of n. Since we usually don't know the standard deviation of our population when we're doing inference, but we can calculate the standard deviation of a sample. So this formula here is generally applied to a sample. So this is generally our sample standard deviation. We just use the sample standard deviation to approximate the population standard deviation. So the central limit theorem is expressed in terms of sigma, which is usually unknown, but the way we calculate our standard error is expressed in terms of S, which we do know if we have a sample. And we can just get stat key to calculate that for us. So this is the formula that we use for estimating standard error when we're doing inference about one mean.